The sanctions were supposed to work. 3 years ago, policymakers in Washington believed they had found a pressure point. Restrict advanced lithography tools. Limit access to cutting-edge chip-making equipment. Prevent the transfer of expertise. Slow China's progress by years, perhaps even a decade. Instead, a new laboratory in Beijing quietly switched on its systems. And inside that facility are engineers who spent years building some of the most sophisticated semiconductor technologies in Europe. Not hundreds of them, not thousands, just enough. Because semiconductor manufacturing has always been a strange industry. It isn't like steel, where more furnaces solve the problem. It isn't even like software, where an army of programmers can eventually brute force a solution. Sometimes the difference between failure and success is a small group of people who know why a machine vibrates at a frequency nobody expected, why a laser drifts out of alignment after 8 hours, or why a process that works perfectly on paper suddenly destroys millions of dollars worth of wafers. And those people carry that knowledge in their heads. That is what makes this story worth paying attention to. We're not talking about espionage. We're talking about recruitment. We're talking about contracts, salaries, research budgets, and laboratories built specifically to attract engineers who spent decades working inside Europe's semiconductor ecosystem. And somewhere in Beijing, a new facility has apparently reached operational status. If that's true, then the conversation about export controls may need to change. Because perhaps the most difficult technology to sanction isn't equipment, it's experience. A report published by the Dutch intelligence service AIVD in 2024 warned that countries seeking semiconductor independence were increasingly targeting highly specialized talent. At roughly the same time, Dutch media outlets began documenting the departure of veteran chip engineers toward Chinese-funded startups and research initiatives. For governments, this creates an awkward dilemma. People aren't machines. You can't place a human being on an export control list simply because they understand plasma etching techniques or have spent 15 years optimizing deposition processes. At least, not easily. There is also another uncomfortable reality. Many of these engineers aren't ideological actors. They're professionals. An engineer nearing retirement who spent 20 years troubleshooting lithography systems might suddenly receive an offer that doubles his salary, funds his own laboratory, and gives him complete freedom to pursue research ideas that his previous employer considered too expensive. Most people would probably take the meeting. Some would sign the contract. And Beijing understands that. China's semiconductor strategy changed noticeably after the October 2022 restrictions imposed by the United States. Initially, there was frustration. Chinese companies still depended heavily on imported equipment. Extreme ultraviolet lithography systems remained unavailable. Several observers concluded that China's ambitions had effectively hit a wall. Yet a curious thing happened. Investment increased. Provincial governments announced new semiconductor funds. Universities expanded engineering programs. Organizations linked to local authorities began searching for experts with very specific backgrounds. Not general chip designers, not software developers. People familiar with metrology. People who understood contamination control. People who knew how advanced process integration actually works. It's almost darkly amusing. Washington spent years trying to stop Chinese access to the most advanced chip-making tools. China responded by looking for the people who had spent their careers learning how those tools behave. Different strategy, same objective. Of course, critics will argue that hiring foreign engineers doesn't automatically solve anything. They're right. One person cannot recreate an entire ecosystem. Even 100 engineers cannot replicate decades of supplier relationships, precision manufacturing culture, and accumulated industrial know-how overnight. Semiconductors are probably the most collaborative products humanity has ever built. Thousands of companies contribute components. Hundreds of suppliers depend on each other. One missing chemical can delay production for months. One unavailable lens can halt an entire assembly line. So perhaps this new laboratory won't matter much. Maybe it becomes another expensive experiment. Maybe Beijing simply collected talented people without giving them the environment they need to succeed. I understand that argument. But I keep coming back to a number: 47. We'll return to that figure later because it may explain why several Western officials are becoming increasingly concerned, not about what China can manufacture today, but about what it might be able to manufacture 5 years from now. And to understand why, we need to leave Beijing for a moment and visit a much smaller place in the Netherlands, where a handful of engineers discovered that their expertise had suddenly become one of the world's most valuable commodities. The town is called Veldhoven. If you follow the global semiconductor industry long enough, you eventually realize that an extraordinary amount of technological leverage sits inside this relatively quiet Dutch municipality. It is home to ASML, the company that became indispensable to advanced chip production because nobody else managed to commercialize extreme ultraviolet lithography. People often describe EUV machines as if they're products. They're closer to ecosystems. More than 100,000 individual parts, mirrors polished to atomic-scale precision, lasers generating droplets of molten tin 50,000 times per second, and suppliers scattered across Europe, Japan, and the United States. A single system can cost more than $350 million. Building one is difficult. Understanding why it works is even harder. This is where our mysterious number from the previous section begins to matter. 47 wasn't the number of engineers who moved to China. It's the approximate number of critical specialists some industry veterans believe are necessary to seed an entirely new research effort around a narrow technological objective. Not enough to recreate ASML, nobody credible believes that, but enough to attack one bottleneck at a time. Think about contamination control. Inside advanced chip fabs, particles measured in nanometers can destroy production batches worth millions of dollars. A technician who spent 15 years learning how to minimize those defects doesn't carry patents home in a briefcase. He carries intuition. He remembers which variables caused failures during experiments that never appeared in scientific papers. He knows which ideas looked promising and quietly died. That kind of knowledge isn't classified. It simply accumulates. One former Dutch semiconductor executive told reporters years ago that talent migration worried him more than reverse engineering. Machines reveal what they do. Engineers remember why they do it. And Beijing appears to have understood this distinction earlier than many Western governments. By 2023, companies connected to China's semiconductor ambitions were recruiting internationally with remarkable precision. They weren't posting generic advertisements asking for chip experts. They wanted vacuum system specialists, process integration engineers, optics researchers, people with experience calibrating high-precision instruments. The pattern suggests a deliberate effort to assemble missing pieces rather than purchase an entire puzzle. An interesting case emerged through the company Sea-Carrier. Outside industry circles, few people had heard its name before sanctions intensified. Yet analysts noticed it steadily attracting engineers with backgrounds linked to European semiconductor suppliers and advanced manufacturing firms. Public information about Sea-Carrier remains limited, which naturally produces speculation. Some observers describe it as a future equipment champion. Others think it serves primarily as an experimental platform where imported expertise can interact with domestic researchers. I'm not completely convinced either explanation captures the full picture. There may be a simpler answer. China doesn't necessarily need another ASML. It may only need organizations capable of reducing dependence in a handful of strategically painful areas. Even partial success changes the equation. Suppose Chinese firms improve metrology capabilities enough to cut foreign imports by 20%. Suppose domestic deposition tools become reliable enough for mature nodes. Suppose packaging technologies continue advancing at their current pace. Individually, none of these developments overturn the semiconductor hierarchy. Together, they begin to erode it. And that's where ordinary people enter the story. Most viewers will never purchase a lithography machine. Probably for the best. They require a clean room, specialized infrastructure, and a maintenance budget larger than many national science programs. But everyone buys products containing chips. Phones, cars, medical equipment, industrial robots, even refrigerators increasingly depend on semiconductors. If supply chains become less concentrated, prices may stabilize. If technological blocks split permanently, costs may rise instead. That isn't abstract geopolitics. That's the price of your next laptop. Western policymakers often defend export controls by arguing they buy time. I think that's accurate. The question is, how much time? 2 years? 5? 10? Nobody seems comfortable answering publicly. And there is another complication. Several European governments face demographic pressures inside high-tech industries. Experienced engineers retire faster than younger specialists replace them. Companies compete aggressively for talent already in short supply. Restricting equipment exports is administratively manageable. Restricting labor mobility inside open societies becomes politically awkward very quickly. After all, what exactly do you tell an engineer? You may work wherever you wish, unless your expertise became geopolitically inconvenient? Democracies generally dislike making that argument. China knows this. It doesn't need every engineer. It only needs enough individuals willing to accept an invitation. Because unlike machines, people eventually decide for themselves where they believe their future looks more interesting. And this is where the story takes an unexpected turn. The biggest challenge facing Beijing may not be access to expertise. It may be convincing those experts to stay long enough to turn laboratory research into industrial reality. History suggests that transition is much harder than recruiting talent. Much harder. There is a temptation to look at a newly operational laboratory and assume the hard part is over. Hire talented people, build modern facilities, purchase whatever equipment remains legally available, wait a few years. Problem solved. Semiconductor history says otherwise. The graveyard of ambitious chip projects is crowded. Japan once dominated memory manufacturing. Europe hoped programs like JESI in the late 1980s would preserve technological leadership. The Soviet Union employed brilliant physicists and engineers, yet struggled to convert scientific achievements into competitive microelectronics. Knowledge matters. Execution matters more. A laboratory can prove a concept. A factory has to repeat that concept millions of times without failure. That distinction sounds boring until you realize it determines whether a country earns billions of dollars or produces little more than academic papers. And this is where my own argument starts becoming less comfortable. I've spent most of this video suggesting that talent migration could gradually weaken the effectiveness of export controls. I still believe that. But perhaps we've been asking the wrong question. Maybe Beijing never expected Dutch engineers to hand over a shortcut toward extreme ultraviolet lithography. Maybe they were recruited for something much more practical: confidence. Think about being a young Chinese process engineer in 2026. You've spent years hearing foreign analysts explain why your country cannot reach the technological frontier. Then suddenly, you're sitting in a laboratory beside someone who spent 20 years solving problems at one of Europe's most sophisticated companies. That changes the atmosphere. Technical advice matters. Psychology matters too. People attempt difficult projects when they believe success is possible. This doesn't guarantee success. It simply raises the probability. And there are reasons for skepticism. China's semiconductor industry still relies heavily on imported components. Precision optics remain extraordinarily difficult to manufacture. Advanced photoresists, high-end inspection tools, and specialized materials continue to present obstacles. Even companies making rapid progress face bottlenecks. SMIC's 7-nanometer production capabilities surprised many analysts, but scaling production economically is an entirely different challenge. Producing demonstration wafers impresses engineers. Producing millions of chips at competitive yields impresses investors. Those aren't the same competition. Then comes the reversal. The laboratory in Beijing may not even represent China's most important objective. Suppose its real purpose is educational. Suppose it functions as a training ground where experienced foreign specialists transfer practical knowledge to hundreds of younger domestic researchers. In that scenario, the laboratory itself becomes almost secondary. Its graduates become the product. 10 years later, those engineers disperse across dozens of Chinese companies, universities, and equipment manufacturers. One improves deposition systems. Another develops inspection software. Someone else redesigns vacuum chambers. Incremental improvements spread outward like ripples. Nobody notices a ripple. people notice a wave. This possibility explains why officials in Europe increasingly discuss knowledge security rather than traditional technology security. They're beginning to recognize that semiconductor competition resembles an apprenticeship system disguised as industrial policy. You can restrict shipments, you can block acquisitions, you can deny licenses. Preventing experienced engineers from sharing ideas over coffee becomes considerably harder. And frankly, democratic societies should be careful here. Scientific collaboration helped make Western technology ecosystems strong in the first place. Closing every door risks damaging the openness that generated many of these advantages. That balance feels fragile. Too much openness invites strategic leakage. Too much restriction encourages isolation and stagnation. Neither path looks particularly attractive. My prediction? By the early 2030s, the semiconductor landscape will probably look less like a pyramid and more like a mountain range. The United States will remain dominant in chip design. Taiwan will still possess manufacturing capabilities few others can match. The Netherlands is unlikely to lose its position in advanced lithography. Yet China may become strong enough across multiple supporting technologies that sanctions gradually lose part of their leverage. Not because Beijing copied everything, because it learned enough. And if that happens, historians may eventually conclude that the most consequential export after 2022 wasn't a machine leaving a warehouse. It was an engineer boarding an airplane with 30 years of experience and a notebook full of ideas. One notebook, one contract, and perhaps the beginning of a very different semiconductor era. Remember that engineer we imagined earlier? The one offered a larger salary, a private laboratory, and the opportunity to pursue ideas that had spent years sitting in a drawer because budgets were tight and managers wanted safer projects. He's not hypothetical anymore. People like him already exist. Some have retired, some commute between Europe and Asia, some accepted positions at Chinese companies and later returned home. Others stayed. A few probably regret the decision, most likely don't. Because engineers, despite the geopolitical narratives built around them, often care about something surprisingly simple. They want to build things. And semiconductor research can be frustratingly slow. Experiments fail, funding disappears, corporate priorities change. Entire projects get abandoned because quarterly earnings matter more than long-term science. If another country walks in and says, "Here is a facility, here is a team, here is 5 years of funding, try again," many researchers will listen. That doesn't make them traitors, it makes them scientists. Still, I don't think Beijing has won this contest. Not yet. Talent acquisition is merely the entrance fee. Turning imported expertise into an independent semiconductor ecosystem requires patience measured in decades. China has shown patience before. High-speed rail looked unrealistic 20 years ago. Commercial shipbuilding was once dominated by other countries. Electric vehicles seemed like an impossible catch-up story until companies such as BYD started forcing competitors to rethink their assumptions. But chips are different, brutally different. A modern semiconductor supply chain depends on trust built over generations. Suppliers share sensitive information because relationships developed over 30 years. Customers commit billions of dollars because equipment manufacturers have demonstrated reliability thousands of times. Mistakes are unforgiving. One defect can ruin an entire production run. One delayed component can idle a fabrication plant costing $20 billion. This is why I remain cautiously skeptical about claims that China will soon replace every foreign technology. That prediction feels premature. At the same time, dismissing Chinese progress simply because sanctions exist also seems detached from reality. We've already seen evidence that pressure can encourage adaptation. Huawei's return with advanced processors surprised people who believed restrictions would completely freeze innovation. SMIC demonstrated capabilities many analysts expected to remain out of reach for longer. Chinese universities are producing increasing numbers of engineering graduates, and somewhere in Beijing, a laboratory reportedly became operational with assistance from specialists who once helped sustain Europe's semiconductor advantage. That matters. Not because it guarantees success, because it proves determination. The larger question isn't whether China will surpass the West. Competition at this level rarely produces a single winner. The better question is whether export controls can preserve technological leadership indefinitely when expertise itself remains mobile. Personally, I doubt it. Leadership survives when countries continue attracting ambitious people, supporting risky research, and maintaining ecosystems where talented engineers believe their best work still lies ahead. Preventing others from advancing can buy breathing room. Using that breathing room wisely is the real challenge. Otherwise, sanctions become a stopwatch. Useful for measuring time, less useful for deciding what to do with it. As for that laboratory in Beijing, perhaps 5 years from now we'll barely remember its name. Or perhaps historians will point to it as one of those moments that seemed insignificant while it was happening and obvious in hindsight. I'm leaning toward the second possibility. Not because China suddenly solved semiconductor manufacturing, it hasn't. Not because Dutch engineers possess magical knowledge, they don't. But because 47 highly experienced specialists working alongside hundreds of younger researchers can create something far more valuable than a machine. They can create confidence, and confidence has a habit of turning impossible projects into ordinary engineering problems. We'll find out soon enough. Until then, the semiconductor race continues, one wafer, one experiment, and apparently one job offer at a time. If you enjoyed spending these minutes with me, stick around for the next discussion. The most interesting stories are usually hiding inside industries people assume are too complicated to matter. Turns out they matter quite a lot.